Hey, everybody. Welcome to Lecture 6. We're going to be talking about statistical theory today. We're working on the normal distribution and the t-test. We've already talked a little bit about the probability and some of the basics that underlie these several statistical concepts, but now we're going to see some of the math and a couple of examples. Um, Reminder that all of this is really useful to know and great background, but I'm not testing you on how to do the normal distribution or how to understand the normal distribution, how to do the t-test by hand. We're not going to be doing it by hand. I'm not going to be making you use any tables or anything like that. We are actually going to just understand this theory and then use it in practice in R because that is what matters. So let me share my screen and we'll do it. Okay. I'm in my campus office today trying to see if I can get this to work. So if it looks weird or something, shoot me an email, and I can try to figure out how to make it better for you. All right, here we go. Normal distribution and the t-test. We've already talked plenty about what a normal distribution is. This is a slide that's basically bringing back that concept from the last time we talked about it, which has been several weeks. The normal distribution is a continuous probability distribution described with a bell curve shape. We also call this a Gaussian if you're in the physical sciences or come from that background. Um, it's a good approximation for the frequency distribution of a lot of biological variables, or at least it's supposed to be. One big assumption that we make is that if we sample properly and we collect enough data, our data should appear approximately normal, right? If we collect enough sample sizes of large enough size, they should be the approximate shape of a normal distribution around our population's mean. So here are some examples of normal distributions. Okay, the probability density function for any value of y is described here. Oops, sorry, I didn't mean to stop sharing. Okay, probability distribution f of y for any value of y is this formula that you see in the bottom of the screen. Uh, it's complicated and it's also a little grainy. Sorry about that. So just a reminder, the pi symbol is pi. When you see an e, that's the base of the natural log, 2.7182. Y is any real number. Mu is the mean of the distribution that we're looking at, and the alpha sigma is the standard deviation of that distribution. So we take any value of y, we plug it into this formula, which is quite complicated, and we're able to generate the function for this probability density or for this black continuous curve. Notably, I'm never going to make you do that. We actually instead are going to learn one line of code where we can do that without really having to do any math. But if you wanted to learn the math, there it is. You could, in theory, make it by hand. All right. The reason that I'm showing you this map is because we want to also talk about some properties of the normal distribution. We've already done this once. We're going to see it again today because seeing stuff multiple times is a great way to learn. So the probability of a thing happening, an event happening, is measured by the area under the curve. It's not measured by the height or the y-axis value. It's measured by the area under the curve from one point to the next. Normal distribution has probability that is symmetrical and a shape that is symmetrical around the mean. The mean is equal to the median is equal to the mode. Usually in a normal sample, those are slightly different because we're not fully, usually in any sample, the mean, median, and mode may be slightly different from one another, but in a normal distribution, the mean, median, and mode are the same number. The most frequent number, the middle number, and the average are all the same. The highest probability of an event occurring is, of course, at the mean because, that's how it's defined. And approximately 2/3 of the data are within one standard deviation of the mean. This is actually not exactly 66%. It's actually 68.3%, but whatever, close enough. So roughly 2/3 of the data are between mu minus sigma and mu plus sigma, or the mean minus the standard deviation and the mean plus the standard deviation. The second thing that's really important here is if we have normality, 95% of the data of the probability, lies within 2 sigma of the mean. 2 standard deviation of the mean, which is the same thing as the standard error of the mean, 2 standard error of the mean, is where 95% of the data lie. So if we have a normal distribution, we have a really good sense for where 5% lies, the last 5%. It's outside of 2 standard deviations away from the mean. That's really useful for us. That p equals 0.05 is, reminder, kind of the cutoff. So if we're looking at a one-tailed test, this is really useful for us. But we have a really good sense for our understanding of how the data are structured if we have a normal distribution. Okay, so to kind of bring this all home, there's a 95% chance that a measurement of a randomly chosen observation from a normal distribution lies within 2 standard deviations of the mean. All right. The reason that this matters is because this standard normal distribution with its known probabilities is the basis for like every single test we're going to learn in statistics this semester. It's the basis for a linear model, for a linear regression, which is really kind of like everything that we're going to learn. The t-test, the analysis of variance, and the linear model, they are basically the same thing. They're just used for different use cases. And we're going to go over that in class and also in these video lectures. But the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So you can see one at the right here. And again, this is from chapter 10 of Whitlock and Schluter, the analysis of biological data. There's a free PDF on the Moodle page, the Lyceum page, sorry. One day I'll get used to that. But you can see that the z-score, or the x-axis, has a mean of 0, standard deviation of 1. 2 standard deviations is minus 2 to 2. It's symmetrical. So the standard normal is the basis for this thing that we call the z-score, which underlies the t-test. Z is used to indicate a variable having a standard normal. Calculating probability of an event in a normal distribution requires something called integration, which you can kind of tell from here. We're doing integration. It's a little bit hard to do by hand. We use tables to do it instead. We can use tables to give us these answers just by looking at these like standard z-score tables. Because this probability is always the same, we know exactly what number is the cutoff for like p less than 0.05 or some such thing, given the sample size that we have. This is kind of an old school way to do it. I'm going to show you how it works. We're not going to do it this way. We are always going to use R because, you know, it is the modern era and programming is the answer. But nonetheless, I want you to understand the theory. So I am going to go through it. Okay. Let's say you're using Z to find the likelihood of something occurring or not, or of significance to happen or not. We have this question: what is the probability of Z being greater than 1.5? That's just 1.5 on the x-axis, right? So we might look for, sorry, oh my God, going backwards. The probability of Z being greater than 1.5. We go to our table, we find the first 2 digits of a.bc, which is totally clear, right? Which is the Z, 1.50 a.bc, 1.5, and then we find the second digit after the decimal, 0. So that's 1.5 and 0. Let me annotate this. We find 1.5 and 0, right? So that's our first 2 digits, and this is our second digit after the decimal. We end up with this probability of 0.0668. I clear these. So if we are asking what's the probability of Z greater than 1.5, which is going to be like here, 0.0668. That is not less than 0.05, notably. But we might ask another question. Like, what's the probability of Z being greater than 2.01? So that's just outside that 95% confidence range. There's the 2. Here's 2.01. So we go down to 2.0 and then 0, and we end up with 2.01. The probability of Z being greater than 2.01 is 0.0222. And I just did 2.00 because I'm bad at this, but you know, 2.0, 2.01. Hopefully you caught that. 2.01, 0.0222. So that's pretty cool. There's our probability. It's really easy to use these tables. What's really, really important here is the following relationship. And this is really the only part that matters a lot, is this bit down here, right? Z equal to 1.96, positive or negative 1.96, gives us a probability of 1.96.250. The reason that that matters is because most of our tests, as we learned last class, are actually two-tailed, right? We're interested in the values that are outside, that are either 2.5% on the high end or 2.5% likely on the low end, right? That's our 95% confidence interval, or 95% cutoff for P equal to 0.05, right? Because the probability of being greater than 1.96 and the probability of being less than 0.96 are both equal. They're both equal to 0.05. And if we're adding our probabilities together, 0.025, we're adding our probabilities together, the probability of being either greater than 1.96 or less than negative 1.96 is equal to 0.025 plus 0.025, which equals 0.05, right? So the p-value 0.05, that cutoff comes where z is plus or minus 1.96, and that's 2.5% on the top end and 2.5% on the low end. So we are looking for, assuming a standard normal, we're looking for these values that are outside of 1.96 on a z-score, right? Okay. Now you've only seen the z-score applied to just a probability density. We're going to carry that forward using examples here in a minute. But I just want to show you. We may also be interested in a bound, right? Calculating a bound of probability. Just so you know, you can do this. We already have seen this. You can calculate the area under the standard normal curve between the lower bound and an upper bound. So the probability of being between two numbers. We've learned how to multiply. We've learned how to add and subtract and divide probabilities. This is how this works. But generally speaking, we can say, what if we want to do bounded probability? We can. Yay. Now, what's more important is that we want to use the standard normal to describe any normal distribution. And the way that this works is we can say it doesn't matter that our mean is like 9,000 as long as we are normally distributed. We know that the standard deviation is plus or minus 1. We can standardize our normal distribution from whatever our true mean is to the value of the mean being 0 and the standard deviation being the same as the standard normal. And thus, we can use the standard normal and the z-score to calculate the probability of stuff happening in our distribution, which is basically how a t-test works, or how any statistical test works. Probably sounds confusing. We can talk about it more in class, but let's do it. Let's say we know that z is the standard normal deviate, the z-score. How many standard deviations a particular value is away from the mean? That's what you can think of a z-score as, in case you hadn't already seen that. So z in this case is just any number, r number, minus the mean divided by the standard deviation. That's how you calculate z. And z, again, is just the number of standard deviations above or below the mean. So let me just show you. I'll go back, and I'll show you that. So see how we have a z of 1.96? Let me get my annotations back out. I'm obviously being an old person here. Z of 1.96 is just really close to z of 2. And this is just one standard deviation and two standard deviations above the mean, right? So z is just simply the number of standard deviations you are away from the mean, positive or negative. All right. So knowing that, we've got our formula for z over here and our example to the right. And our example is, who can or can't be a NASA pilot? NASA requires people who want to be pilots for them to be taller than 157.5 centimeters and shorter than 190.5 centimeters. So we have a hypothetical population of people here with a mean height of 177.6 centimeters and a sigma, or a standard deviation, of 9.7 centimeters. So that means one standard deviation. So we make 177.6 the 0. One standard deviation up is 9.7 plus 177.6. 2 would be you add another 9.7. 3, you add another 9.7. The other direction, you subtract those 9.7s. So we're going to write a bounded probability. We want to know what's the probability of your height being less than 157.5 or greater than 190.5, because those are the people who can't fly for NASA. So to calculate our z-score, we take our number. My annotations back out. We take our numbers, which are 157.5 and 190.5, and we do subtraction. 157.5 minus 177.6, that's the mean. 190.5 minus the mean, and then divided by the sigma, which we have figured out here is 9.7, right? And then we get to figure out what the probability of being too tall or too short is. And we end up with the probability of being too tall, 1.33 standard deviations above the mean is our z-score. The z-score for being too short is minus 2.07 standard deviations below the mean. We can then look at our table of z-scores and we can figure out what those correspond to. So let's look at our table of z-scores. Reminder that we have 1.33 above. So let's find 1.33. 1.33. So the probability of being too tall is 0.9176, or about 9%. And the probability of being too short is 2.07 below the mean. And we're using the absolute value. So 2.07 is here, 0.1923. So about 2% of chance of being too short. So there's a decent range in our population that are going to be able to fly for NASA. But the folks that are too tall or too short, we're going to say what's the probability of being too tall or being too short. And we know that that's 0.0979176 plus 0.01923, right? So we have an 11.1% chance of being too short or too tall. So 11.1% of our population that we sampled cannot fly for NASA. We probably have too small of a class to go ahead and do this on our own, but we can think about it in class who's too short or too tall to fly for NASA. I'm too tall, I think. I'm actually going to check right now because I want to know. What is 190.5 in freedom units? Imperial units. So it's actually 6'3". So I'm not too tall. I'm 6'1.5". So I can fly for NASA, I guess. I'm sure there's other reasons why I can't. All right, moving on. That's an example of how to use the z-score, by the way, to find probabilities. So we take our normal distribution of data that we have any value for the mean, and we know that it fits the normal distribution. So we can put that value of 177 or whatever right at 0. And when we have the deviation, the standard deviation, we can then basically use our z-scores to find the probability of anything in our distribution. Knowing that, we can then also use the normal distribution to approximate a mean. If our variables are normally distributed within a population, then the true value of the population also has a mean of y. Okay, wow, botched that. So using the normal distribution to approximate a mean. If a variable, let's say y, has a normal distribution within a population, then so does the mean of y. So if y, let's say y is, it looks like we're using examples. If y is weight, and it's normally distributed in the population, then the mean of y is also normally distributed. So that's what we have on the right here. Let's look at it. And you'll remember this from when we did sampling. If we take a sample of n equals 10, you can see this at the bottom right. Take an sample of n equals 10. Okay, like this. We get a normal distribution. We get a mean when we calculate the mean of our 10 samples of 3084. The true mean of the population is 3339. But if we sample the population and calculate the mean of many different samples, we should arrive at this population level mean, right? So if we take a sample of 10, we get this mean and it's a little bit off. If we take this sample of 100, we get a different mean and it's a little bit more precise. And if we take a sample of 1,000, we get this other mean and it's considerably more precise. And our standard deviation will drop over and over and over again so that we have more precision when we have larger samples, right? And if we were to take, instead of multiple sample, or instead of really large one sample, if we were to take a whole bunch of samples of 10, the same thing would happen, where we would see our mean become more true to the population level mean that we usually don't know. And then we would see our standard deviation shrinking and shrinking. And that allows us to approximate means of populations without knowing the true mean of the population if we take large enough samples and we have normally distributed data. So the distribution of means we would get is normally distributed. We thus call the distribution of means when we take multiple samples of 10. If I take 10 samples of 10 and calculate the mean, the distribution around the mean, the distribution of means that I get, that is my standard error of the mean, or the standard deviation around my mean. Remember that the standard error of the mean is the standard deviation of the population level mean divided by the square root of the sample size. Knowing the population level mean is almost impossible unless we know it beforehand, which why are we doing this if we know it beforehand? We're going to have to approximate it. And this can get confusing. The textbook goes into detail on it, but you can essentially take, if you have a high enough sample size, your sample mean here instead. Okay. All right. Now let's talk about calculating probabilities of sample means. And this is where I'm going to apply some of the math we've just talked about. And I know this is confusing and that I've also made a couple of errors, but I've tried to correct them. But we're going to go over this again and again and again and again in class because this is kind of the basis of stats. And also, I will point out once again that interpreting it is more important than knowing how to do every single step because, to be honest, R does most of these steps for us. So how do we calculate probabilities of sample means? If Z is equal to the sample mean minus the true mean divided by the standard error of the mean, which is true, then Z is the number of standard errors that the sample mean is above or below the true mean. Okay, so now we're not talking about standard deviation in a normal distribution. We're talking about a normal distribution of means. And we have a mean value, a normal distribution of mean values from many samples. And then we have a mean of those means, right? Z is the number of standard errors, in this case, that the sample mean is above or below the true mean. This allows us to estimate where the mean is for many samples within a population, not just looking at any value within a distribution, but the mean itself. This is important, basically because this measure of mean versus like the signal versus noise or the amount of spread we have in the data, we can compare one mean and error to another mean and error and see, do they overlap or not? Are they different or are they not? And that's really what we're getting at with most of our statistical tests, especially when we're thinking about t-test and later ANOVA. Linear models will work the same way, but we'll have to get into that next time. Central to all of this, is the central limit theorem. The central limit theorem, which you've probably heard before, but almost certainly have forgotten by now, says the sum or mean of a large number of measurements randomly sampled from a non-normal population is approximately normally distributed. If you want to put this in simpler terms, we've already said this a lot. You can also call the central limit theorem the law of large numbers with sufficiently large sample size. We're good. And that's all you need to know. So CLT, or the central limit theorem, is why we like large sample sizes. The definition of large is totally arbitrary and depends upon the population, the distribution, and a lot of other things. You're going to have to think about it. It's pretty subjective and varies by the field. We can talk about what you think large is in class. I think that would be a useful exercise. For me, in ecological studies, nothing smaller than 5. You can do stats on anything that's 3 or higher. 3 samples or higher because you need 3 values to calculate deviation. But 5, 7, 9, something like that should be your low end, and like 12, 15, 17, 20. Those are okay numbers. N equals 30 tends to be really good. N equals 100 is, of course, better, but that's not always easy. So here we go. We can take a look at mean age at death in years, and we can look at multiple samples. We take 1 sample, we get this really goofy thing. We take 2 samples, it's already looking pretty good. We take 4 samples, it's looking even better. We take 64 samples, we have a perfect normal distribution, right? So if we're looking to find the mean of something, if we take a bunch of samples of that thing, of that population, we're probably going to get pretty close to approximating that mean as a normal distribution. So this is why, even though your data may not individually be normally distributed, and even though the data in your population may not be normally distributed, if you take enough samples, you should have a normally distributed mean range. That's what we're after, because we're really trying to compare the center and spread, right? The mean and variance of your data. All right, now we're going to apply this concept of Z to something called the T distribution. We're going to use this to do basically a t-test. So here we go. When we try to calculate Z, we need the standard deviation of the true population mean. You basically can't get that. We don't know the true population mean just about ever, which means we kind of can't know the true population standard deviation either. Unless we can sample every individual within our population, we're almost never going to have Z because we don't have the sample mean. Sorry, we don't have the true mean and we don't have the error of the sample mean. Oh, sorry, we don't have the standard deviation of the true mean. Because we lack the data on the full population, Z must be approximated. And that is where the T distribution comes in. So here's some math. Z is equal to the sample mean minus the true mean divided by the standard error of the sample mean. That's fine. We don't have the true mean ever. The standard error of the sample mean is the standard deviation of the population mean, the full population mean divided by the square root of n. Again, we never have the full population mean. So here, this is great math and all, but we never have this value and we never have this value either, this value. So what do we do? Do we just guess? Like, obviously that's bad, right? This is the basis of all of our assumptions. And if we like guess numbers or we put in the wrong numbers, everything we do is going to be wrong. So there is a clever way to get around this with some unique math. We can use an approximation for standard error, which is standard error of the sample divided by the square root of n, sample size instead. We already talked about this briefly, but we can use this approximation for standard error instead. And if we do that, we're no longer calculating the Z distribution. We are now calculating the T distribution. And it's just like a slightly modified version of Z that accounts for a little bit of wiggle room or error that we would get from making this assumption. So now we're calculating T, or the student's T. And you've probably heard that before. Maybe you've done it before, but this is what happens. You apply your Z concept to the T distribution with this assumption for standard error, where we're not looking at the population level standard deviation. We're looking at the standard deviation of just our sample. So T, very much like Z, is equal to the sample mean minus the population mean divided by the standard error with this assumption. Standard error is standard deviation of the sample divided by the square root of n. So I'll show you a T distribution in just a second, but first we need to talk about the concept of degrees of freedom, and then we can look at some distributions and examples, and we are working our way to the end of this, I promise. Degrees of freedom, or DF, you almost certainly know what this is. It's n minus 1. There's a bunch of reasons for it. We'll talk about it. It's basically the sample size. So the sample mean minus the population mean divided by the standard error has a student's T distribution with n minus 1 degrees of freedom. We generally think of degrees of freedom as n minus 1 instead of as n, and this is because it's a conservative estimate. The value for degrees of freedom tells us which version of the T distribution we need. In other words, it tells us which table to use, or it tells R which table to use. There's different tables for the T distribution based on degrees of freedom. The reason for that is that different sample sizes give us different probabilities. It slightly modifies our data, slightly modifies our distribution. And we use n minus 1 instead of n because if we subtract 1, it makes this denominator smaller, which gives us a little bit more error or a little bit more variance. So it's a way to account for some of the assumptions that we're making, like that assumption about standard error. I guess I wrote that in. You can read it if you didn't want to. If you didn't believe me when I said it, you can read it. This is straight out of the textbook. We're estimating the parameter, the standard deviation of the true population. As a result, we're going to be less accurate. So we are going to be a little conservative by doing n minus 1 instead of n in the denominator. Okay, now, how do you compare Z and T? The answer is they are almost exactly identical, but you can see from this graph that they are slightly different, right? So there's a little bit of an approximation being made with t, and as a result, you end up with like a little bit less confidence for a mean and a little bit more variance at the tail, right? The t distribution is slightly fatter in the tails due to n minus 1 degrees of freedom, and it's slightly less accurate than the z, but it's a basic approximation for a z-score. It's the same idea with just one assumption that modifies it slightly. You're going to see this motif over and over again this semester because the linear model and the ANOVA are based on similar concepts with F distributions instead of T. Slightly different. We're going to get there. So if you understand that this has happened where there's a slight difference in how Z and T work and Y, you're all set for theory. When we use the T for statistical tests, we pretty much always want to find this thing called the 5% critical value of T. That's the same thing as what we just did for that 1.96 Z equals 1.96 thing. That's the critical value. If Z is greater than 1.96 or greater than the absolute value of 1.96, we're at the 5% critical value. This varies based on degrees of freedom with T. We can use R, or we can get a table. We can use a table to get this. Here you see an example. In this example, this is the T if our degrees of freedom are 4. That means we have a sample size of 5. That is not very big. With a degrees of freedom of 4, you can see that the critical points for 2.5 high or 2.5 low, that's 2.78, a T of 2.78. You can get this value from a table, and hopefully I have a table for you to look at. Yeah, here you go. It's like not super interesting, but here's the table. And this is what underlies how R makes decisions about statistical significance. We have our degrees of freedom here, and it keeps going. I just stopped. And you can see that we can look at critical values. We can say, what's the critical value? This is a one-tailed T and a two-tailed T. They have the same critical values. Okay. We're looking for a two-tailed T with 0.05. That's here. We have 4 degrees of freedom. That's here. So it's 2.78. Anytime T is greater than the absolute value of 2.78, we have statistical significance. Okay. So let's try to apply that. That's on a 2-sample t-test. Notably, you can also do a 1-sample t-test. And I'm going to show you a 1-sample t-test first, just because it's supposed to be simpler. So let's compare the mean of a random sample from a normal. The 1-sample t-test allows us to do the following thing. We can compare the mean of a random sample from a normal population with the population mean proposed in the null hypothesis. So we might say the true mean of the population equals some number. The alternative might be the true mean of the population does not equal some number, and some number in our case is the mean of our sample. The true mean of the population equals the population level mean. I think that is actually the wrong thing. We're saying the true mean and the sample mean are the same, basically. Compares mean of a random sample from a normal population with the population mean proposed in the null hypothesis. So does our random sample mean equal our proposed mean? Yes or no, basically. The H naught, the null hypothesis, is they are equal. So then we do this. For our test statistic, we say T equals the sample mean minus the population mean proposed by the hypothesis divided by the standard error of the sample mean. Okay? Let's do it. Null hypothesis, the mean human body temperature is 98.6. Alternative hypothesis, it's not 98.6. We have 25 samples. N equals 20. Hello. N equals 25. That means degrees of freedom equals 24. We happen to know that our sample mean from our sample of 25 is 98.524. Now, is that different than 98.6? We know our standard deviation is 6.78. We calculated our standard error. So that's the standard deviation divided by the square root of the sample size, 0.36. So sorry. T, as we know, is just our sample mean minus the proposed H naught mean divided by our standard error. We get a value of negative 0.56. So our T is equal to negative 0.56. Is negative 0.56 significantly different from 0 such that we should reject H naught? A perfect match between our populations would give us a t equal to 0. But we need to see, is this very unlikely? 0.56. So we have a one-tailed negative t-test. We have a one-tailed t-test. Can we reject H naught? We need a p-value to check. Okay. So what's the probability of obtaining a result as extreme or more extreme than our t? We say the probability is 2 times the probability of t less than 0.056 plus the probability of t greater than 0.56. That 2 shouldn't be there. That's not correct. Okay. The probability that we're looking for is t less than 0.56 or greater than 0.56. And that's equal to the probability of 2 times it greater because it's the same value since it's symmetrical. Next, we calculate the p and we need r. To do this, we can type into r, what's 2 times 1 minus this? PT Q equals abs 0.56, degrees of freedom equals 24. So we're saying like, what's the probability of this happening? And we get the probability is 58%, 0.58. Or we can use table C in our textbook. And if we do that, what we're going to find here, we have 24 degrees of freedom. We're looking for P 0.05. And this is actually not a one-sided example. This is a one sample T. We've only taken one sample. It's not one-sided, it's one sample. We've only taken one sample. Okay. We're still using a two-tailed T. We're going here. We're going here. 2.06. If we want to have significant difference from 0, T needs to equal 2.06. It does not, right? That means our sample mean and our population mean are not statistically different from one another. All right, here you go. P equals 0.58. We calculated that here, which is greater than 0.05, unless we fail to reject our null hypothesis. Or we used the table and we found that the T is equal to 0.56, which is less than 2.06, which means that P is greater than 0.05, and we fail to reject our null. We'll always use R to calculate these values, but now you've seen how to do it twice. I'm going to go over it again just because I think I wasn't super, super clear and I feel kind of bad about it. So what if we did this math, we calculated our mean, we have our mean, our standard error, all that. We're ready to figure out, we have our T value of 0.56, negative 0.56. We want to see if this is giving us evidence that we can reject our null hypothesis that our temperature that we measured and the body temperature of a human are different. So let's find a p-value, or at least do the probability check with our table. First, we can do it in R. We know how to calculate probability. So we type this little math equation into R, and it gives us a p-value. It tells us the p-value is 0.58. 0.58 is greater than 0.05. That means we do not have a significant difference between our mean and the population level mean that we said was real. We can also use the table in our textbook to look for a critical value. And we basically will find that the critical value, or T, has to be greater than or equal to 2.06 for us to get differences between our two values. And we do not have that value. So we can fail to reject our null, which basically means we have no evidence that the population level mean and the value that we measured from our sample are different. That's it. That is a t-test, and it's all done by hand that way. There are way easier ways to do it, and I hope that I'm showing you one next. I did not show you one next. I will show you one in class if there isn't one coming up right after this slide. Let me check. There's not. Cool. So in our lab where we do t-tests, and on the Lyceum page, there's a link to the website where I lay out how to do all this stuff. There's a really easy way to do a t-test with one line of code. All this stuff that we just did happens kind of automatically, but we need to know what's happening. This is just like my rule about ChatGPT. It's totally fine to use it. It's totally fine. It's great. It's the ideal thing to do, to use R. So it's totally fine to use ChatGPT. We just have to know what the assumptions are. It's totally fine to use R to do stats. We just have to know what the assumptions are. So here we go. The assumptions for the one sample t-test, which is what we usually do, the data are a random sample from the population. Are the data randomly sampled? You can't really test for that in R. You need to know something about how the samples were collected. So that's really important to check. Number two, the variable is normally distributed in the population. So we need to look at a histogram of our samples. And we're also not going to know if the variable is normally distributed in our population necessarily. So you might be asking, like, what do I do about these assumptions? How do we test them? This is how. We can sometimes ignore our assumptions. We're going to talk more about this later. In the lab in class, we are going to talk through some of these assumptions, how to test them, how to know when we don't need to test them, and what we can do about them. And the short answer is that there's a version of t-test in R that's kind of the default t-test that is robust to assumption violations, which means we can use it even if we don't have all this stuff. All right, next. Quick terminology review, and then we're done, which is good because my brain hurts, which means, probably all of our brains hurt a little bit. The population level mean is the true mean of an entire population, different from the sample mean. A sample is a sample of that population. It's hopefully random. We aren't 100% sure all the time, but we're going to do our best. The sample mean is the mean of our sample. It's likely at least a little bit different numerically from the true population mean, but it might not be significantly different from the true population mean. We have to do a test to figure that out. Variance is a measure of spread. We learned this last class, and it is that math there. It's the sum of some number minus the population mean squared divided by n minus 1. That equals s squared. Now, the square root of that is our standard deviation, which is just s, a measure of spread. The standard error, of course, is slightly different from that, and it is a measure of the confidence that your sample mean matches the true mean. And it's the standard deviation of the sample divided by the square root of n. Remember that it's actually supposed to be the standard deviation of the true population mean divided by the square root of n, but we don't know the true population mean, and thus we don't know the true population deviation. But instead, we can substitute the true population mean for the standard deviation of our sample. And if we do that, we then have to use the n minus 1 for degrees of freedom and the t distribution instead of the z distribution. Super clear, I'm sure. We'll go over that again. We also talked about this thing called the confidence interval. We didn't really see how to measure it yet, but it's usually a 95% thing. And it's a measure of confidence that the value you are describing lies within certain bounds. We probably won't get to this at all this semester, how to actually calculate these things, but they can be approximated in a relatively straightforward way. Like this. We already know we can approximate a 95% confidence interval by doing 2 times the standard deviation of our mean when we have normal distributions. If you want to see how to do more math behind a true calculation of the confidence interval, we need to look at chapter 11 of the Whitlock and Schluter textbook. You're welcome to check that out. I can also send you a link to where I'm showing people how to do that via something called bootstrapping. I didn't put that on our course website, but I do have some code that I've written and a tutorial that I've written in R for people who are ready to try to take that step, but we're probably not going to get there this semester. Quick reminder, this is not for you. Okay, now we've gone through the 1 sample experiment. We need to talk about a 2 sample experiment. And this is a paired t-test. I'll walk you through it. It's basically the same idea. Let's say we're doing a 2 sample experiment. Both treatments are applied to every sample unit if we have a paired experiment. And what that looks like is instead of having paired measurements are converted to a single measurement by taking the difference between them. We can then calculate the mean difference to assess the effects using a paired test. So we have a 2 sample T or a 2 sample test. We would have like an orange and a yellow treatment, and the oranges and the yellows are separated from one another randomly. They're randomly distributed across our grid of whatever, say the intertidal. We have these little boxes, and these boxes are enclosures where we're doing exclusion of something and exclusion of something else. Or let's say orange is exclusion and yellow is just no exclusion. Control versus treatment. We have them randomly distributed. Now, that's great and all, but we've probably also learned that a little bit more systemic design is nice. So here's a paired example where we have the yellows and the oranges next to each other. So we have a grid with a block down the middle, and one half is the control and the other half is the exclusion. So we can right next to each other where everything is roughly the same, see how things play out. So this is how you do a 2 sample or a paired experiment. Okay, Each treatment is composed of an independent sample, random sample of units. Here we can, this is the two sample. I'm just having a little bit of a brain day today. So sorry. I explained paired when I was looking at the graph. I explained two sample when I was looking at the graph as well. We can use a paired t-test for the paired example. We can use a two sample t-test when we have two different treatments kind of randomly distributed. So two sample, each treatment is composed of an independent random sample of units. We can calculate means of each treatment separately, and we can compare them with a two sample test. This is how we normally do a t-test. We have one population over here that's doing one thing and another population over here that's doing another thing. We can use a two sample t-test to see which ones are different from each other. In a paired test, instead of doing a two sample, you do a one sample t-test. But when the plots are paired like they're paired in this example, you actually subtract, you calculate the difference between the plots. And you then do a one sample test to see if there is a difference, to see if there's significant statistical significance related to the difference between the plots. Okay. I think I have an example of each. With the paired test, which is coming up first, this is what you do. The mean change in some variable after treatment was 0. So here in our example, we might be measuring like we have this plot and all these other plots, and we're measuring like what's the effect of the orange treatment relative to the yellow control. So we basically do an effect size here. So orange minus yellow, the difference. So we're then saying, whoops, the mean change in variable after treatment was 0. And the alternative would be it was not 0. So it's still two-tailed. We could go positive or negative. It could be a positive effect or a negative effect of treatment. And we set it up like this. T, sample mean minus the predicted mean, which in this case is just 0 divided by the standard error of the sample. Okay. H naught mean is normally 0 because we're assuming we're doing a difference. So we're calculating the mean difference minus the predicted mean difference. So sample mean difference is some value. The predicted mean difference is 0. So some value divided by the standard error of the sample. It's usually two-tailed. We use T to calculate P. We can do it in R. We can also look at a table. That's how we would do a paired t-test. So remember, if you have paired units like that, you actually have to calculate the difference between the treatment and the control, or between the two treatments. If there's just two treatments, you should use one of those treatments as a control, though, as we've learned. And then you can calculate T, and you can do a test to see, like, is the mean change different from 0? That's what a paired test allows you to do. If P is less than 0.05, we can reject our H naught. The assumptions are the sampling units, not unites, the sampling units are randomly sampled, and the paired differences have a normal distribution. Same as everything for a t-test. These are always the same assumptions. Random sample, normality. Okay, the two sample t-test. That's if we have one population that's one treatment and another population that's another treatment, and they're not paired. We can use this to compare the means of exactly two populations, two independent groups. Notably, I'm going to go ahead and just like point out the most important part. Exactly two. A t-test is only useful for exactly two populations. That means it has very limited use. And you almost never will use it, to be honest, because how often do you just have two populations? We usually don't. You could have treatment and control. That's great for you. But usually we have more than one variable and usually more than one species. So you're going to need an expanded version of t-test most of the time, and we call that the analysis of variance. We're going to dig into that in a couple of weeks. But let's say we have exactly two populations. Our H naught here for our two sample t-test, which is the one we're going to usually do, is that the mean of population 1 is not equal to the mean of population, or is equal to the mean of population 2. The alternative would be that they're not equal. Notably, if you're new to this kind of notation, exclamation point equal sign means not equal. Okay, so now we just do the standard stuff. To calculate T, we do the mean of sample 1 minus the mean of sample 2 divided by the standard error of the difference between the two samples. So the standard error of the difference between 1 and 2. That gives us T. We can use T and our table and our sample size to calculate what we need, and we're good to go. If you needed it, here is the standard error of population 1 minus population 2. It's the square root of the pooled sample variance times 1 over n minus, or n1 plus 1 over n2. Those are the sample sizes. a little bit annoying to calculate, but thankfully we have R. The pooled sample variance looks like this. Uh, so it gets really complicated when you start doing this stuff. And you can now see why we use R, because this is basically the simplest piece of statistics that we're ever going to do. But this is all sorts of kinds of math, right? Do you really want to calculate that by hand and then plug it into this formula and then plug it into this formula and then plug that formula into this formula just so you can get this and then calculate t and then use t to look through a table to get some value for p? Do you really want to do that by hand? It'll take you like, today or all of this week. Instead, if you have your data in the right shape with one line of code in R, in about 2 seconds, you can get your answer. So that's why we like R. Yay, R. Thanks for making our lives easier and better. Okay. As with all other t-tests, we will compute t, use a table to find a critical value, or we'll use a computer, R, to compute our exact p-value. If p is less than 0.05, we reject the h-naught, saying that the population level means are in fact different from one another. That's what we were after this whole time. I've been talking for like an hour about how to do this. And we've been through lots of theory and lots of math. But the general idea is we want to figure out, is population number 1 different from population number 2? We can make a graph and we can do stats and we compare the graph and the stats together with some brain power and we can decide what the answer is. We will be talking about how to do that. We've already learned a little bit about how to make good graphs. We're now going to try to pair graphs with stats, because pairing graphs with stats is how you use all of the tools in your toolkit to really get at the answer to a problem. And that is what we want to do in this class. And that's what we want scientists to do in general. It's good communication. It's clear. It's the way we want to go. So with the 2-sample t-test, we have 3 assumptions. 1, each of the samples is a random sample from its population, hard to measure. 2, the numerical variable is normally distributed in each population. We check for normality. 3, the standard deviation of the numerical variable is the same in both populations. This is a new concept for us. The other t-test we had only had 2 assumptions. But because we have 2 separate populations, we now need the deviations to be roughly equal. This is called homogeneity of variance. Again, there's more on this in the lab. We're going to learn how to test these assumptions. Maybe you already have some ideas. Maybe you are just like, what if we just have big enough sample sizes? Can we ignore everything? And the answer is yes, we kind of can. All right. So when variance isn't homogeneous, which happens often, we have to use something called a Welch's t-test. It's almost exactly the same as the regular t-test, but it's more robust than a normal 2-sample t-test is. There's no harm in using it all the time. And the standard t-test in R is actually a Welch's t-test. You have to tell it to not be a Welch's t-test. So R is going to help you out by assuming that your assumptions are violated, and it's using a more conservative test. So when you use a t-test in R, usually you use a Welch's, and that is all you need. Okay, so what we're really after here is understanding these kind of graphs. Some quick interpretation. We have group 1 with mean and 95% confidence interval. We have group 2 with mean and 95% confidence interval. Group 1 differs from 0. You can see it with our eyes. That 95% confidence interval doesn't overlap that dash, which is 0. Then we have a difference from 0. If the confidence interval does contain 0, the group probably doesn't differ from 0. That's it. Does group 1 differ from group 2? We're supposed to be comparing means and variances. So think about that one. Is this even the best way to analyze these data? Think about that. The answer is really like no. Instead of comparing, does this one differ from 0 and does this one differ from 0? And then saying, since group 1 does differ from 0, it's therefore different from group 2, which is 0 because the confidence interval overlaps 0. That is not the appropriate way to compare if these are different from one another. We can compare whether they're different from 0 individually, and then we can also compare whether they're different from each other individually. And that's what we would use a t-test for. So we could use our t-test here to compare them directly. Here's some more interpretation. Do you see differences or not? These are 95% confidence intervals. I'm not going to tell you the answer. you should check it out. I'm going to zoom right through the answers real quick, but think about it a little bit and compare your answers to the answers that appear here. Okay. Those answers are there. I'm just going to leave this up for you if you want to think about it and then like take a look and see if you can understand why your answer is incorrect, or compare whether you actually got it right. That is it for for t-tests. We're going to talk about linear regression next time. Thanks, y'all.